Good afternoon, everyone, and welcome to our talk. I'm Nicolas Navet from the University of Luxembourg, and this is a joint work with Tieu with a PhD student now. So this work is about the use of machine learning in the design of real-time systems. Precisely, we propose a set of improvements to a deep learning model which predicts the feasibility of Ethernet networks that are using priority as the QoS mechanism. So feasibility analysis becomes a classification problem. The machine learning model classifies configurations as feasible or unfeasible. Now, what's the usefulness of this? Well, a first use case of machine learning is to speed up the verification by replacing simulation or schedulability analysis by prediction. And the speed up factor can be significant, several orders of magnitude, for instance, in this work. So, of course, the machine learning algorithm will be wrong occasionally. So it means that anyway, the final solution must undergo conventional schedulability analysis. But still, the design space exploration can leverage on machine learning techniques. For instance, the combinatorial problem of allocating the software components to the processors is a problem that typically could benefit from machine learning, as well as another problem which we have been working on in our group, which is the comparison of different design options, for instance, in terms of their extensibility, that is their capability to support additional workload later in the lifetime of a system. A second use case of machine learning is the derivation of configuration algorithms without the need for extensive domain knowledge. Like you know, it takes a lot of time to develop configuration algorithms for new technologies. So here the idea would be to automate the process, for instance, by learning efficient strategies over repeated experiments. But this is a problem which is probably harder than classification. So in this work, we are iteratively improving a graph neural network model whose purpose is to predict whether a given priority allocation algorithm, OPA here, using a given schedulability analysis will return a feasible priority allocation. The same model can be reused with other priority allocation algorithms and other schedulability analysis as long as the training sets are labeled using this algorithm. It should be pointed out that the model predicts whether there is a feasible priority allocation, but it actually does not derive it. So the safety risks that could be with false positives, configuration predicted feasible while actually they are not, this risk does not exist as standard verification techniques must be used anyway for the final configuration. However, it's important that the deep learning model is as accurate as possible, otherwise the design choices made using it might be very suboptimal. And improving the accuracy of the prediction model is the motivation of this work. So the rest of the presentation is structured in three parts. First, there is a recap of the GNN model, which aims to give you the intuition of how the raw data defining a network configuration is encoded and iteratively transformed into data that can be used for prediction. Then we present improvements made to the training set, for instance, by over-representing configurations that we know are hard to predict, and improvement to the model itself by introducing new mechanisms like multiple channels and a technique called global pooling. Finally, we study the gains there is to use scaled-up versions of the model and the training set. And now I'll hand over to Tieu for the presentation of the actual technical contribution.
Thank you very much, Professor Nicolas Navet, for the very nice introduction. Next, I will summarize our previous studies. First, with conventional machine learning model that use the manual feature selection approach, as well as its limitation, and that's why we need the graph neural network model to automate the feature engineering step. Back to RTNS 2019, we have introduced the conventional machine learning model based on manual feature selection approach. In this approach, given a set of distinct configurations, we choose the best feature for the configurations. Then we use these feature vectors to train the machine learning model. However, this approach has the limitation that it does not generalize to unseen topologies and unseen traffic. It is because we do not use all the information available. We only choose the best feature. In order to overcome the limitation of the conventional machine learning models, in the recent study, we have introduced the graph neural network model. Given this network, including the nodes, the switch, the links, and the flows, we encode this network to become a graph in which the duplex links, the waiting queues at the egress port, and the flows will be encoded as nodes in the graph. Each node will have initial embeddings. And we also have the connection matrix to show the connections between the nodes in the graph. Then the GNN model will update the embedding using a neural network. And then later we'll aggregate the information from the embedding to become a global attribute that represent the whole graph and update the global attribute vector by another neural network. This step can be done several times. Then finally, we use the model. We use the updated global attribute vector to predict the feasibility of the TSN network. In the next slides, I will give more details in how the GNN model can update the embeddings of the node and the global attribute. When we encode the TSN network as a graph, each node in the graph will have an initial embedding vector. For instance, the initial embedding vector of a flow will be characteristic of that flow, like a payload, period, a deadline, and we scale it to the range 0 to 1. We also have a global attribute vector to represent the whole graph. It is initialized with all 0. Then the embeddings and the global attribute will be updated with the following step. First, we update the embedding of the nodes. By the way, that we will aggregate the information from the neighbor node and as well as the global attribute. We concatenate it to become just one vector, and we update it by a neural network. To update the global attribute, we will aggregate the information from all the nodes, and we give it to another neural network in order to update it. The connection matrix is fixed in this step because the topology does not change. Finally, once we finish this step, we have an updated global attribute, and another neural network is we'll use it to predict the feasibility of this network. So in total, we will have 3 neural networks involved in the GNN model. Now we know how the GNN model works. Next, we need a training set to train the model, as well as the testing sets to see how the GNN model performs. For the training set, we have 10,000 configurations with the random star-shaped topologies, and the configurations is labeled. They are labeled with the precise analysis. For the testing set, we have 13 testing sets. Each set will have 1,000 configurations, and they include the realistic automotive topologies as follows. Some testing sets will have star-shaped topologies. Some follow the chrono topologies, the ring topologies, the backbone, dumbbell, or the Volvo topologies. So the varieties in the topologies of the testing set is very important to test whether the GNN model can generalize to unseen topologies or not. And here's the result of the GNN model. The order from left to right reflects how different it is from the training set and the testing sets. Some very first testing sets have similar star-shaped topologies in the training set. However, on the right hand, it will be different with the marine, bed-borne, or dumbbell topology. In the experiment, we generate 32 GNN models. All of the models are trained with the same training set, but they are different in the initialization of the neural network in the model. And so that they perform differently on the testing sets. And so it's makes some uncertainty of the model. So in order to control the uncertainty of the GNN model, so we propose to use the ensemble of this model. In the graph, the performance of the ensemble is denoted as the green and the blue dots. The experimental results show that the ensemble of 32 GNN models is faster than schedulability analysis at least 70 times, at least 77 times, and up to more than 1,700 times, with the accuracies from 79.3% up to 90%. We also observed that the range of the accuracies of the GNN model will be just in a narrow range from around 80 to 90%. However, for the conventional machine learning model like KNN and gradient boosting, sometimes they have very, very low prediction accuracy. And this proved that the GNN model really generalized better to unseen topologies than the conventional machine learning model. During the development and the experiment of the GNN model, besides its advantages, we also recognize some of the limitations of the GNN model, which leads us to this study of so that we want to improve the performance of the GNN model. First, we will improve the training set with the two-step. The training topologies will be totally random, and we choose the number of flow to focus on the area that is hard to predict, which we will explain in more detail in the next slides. And we also improve the GNN model to choose the better activation function. We try to apply with multiple channel and global pooling to replace the final neural network in predicting the feasibility of the T-state networks. First, we start with the improvement on the training set. This figure show the feasibility proportion versus the number of flows on a testing set that is very different from the training set. And this clearly show the problem that we have the low prediction accuracies on non-star-shaped topologies, which is different from the training set for the GNN model. And the solution for this problem is that we will generate the training topologies that are totally random. So it's not just only star-shaped topologies. And second, we observed that the high false prediction rate is happen on the specific range of the flows, because this is the area that is very hard to predict. And the solution is that we will generate a training configuration and we choose the number of flows to focus on the area that is hard to predict, and so that the GNN model has more chance to learn from this configuration. Next is the improvement on the GNN model. Given the base GNN model, we will use the beta activation function, which is ELU in this study. We also try to increase the number of channels from 1 to 4 channels, but it's does not improve the accuracy, so we just keep the single layer, that's single channel. And we replaced the final neural network to predict the feasibility of the TSN network with the global attribute layer. And so we can predict the feasibility directly from the global attribute. And so we reduce the complexity of the model in total. Besides the improvement on the training set and the GNN model, we also try to expand the model and the training set to explore the possibilities to further improve the performance of the model. We try to expand the training set by double the number of training configurations from 10,000 to 20,000. And for the GNN model, we propose we try to increase the size of the embedded vector from 16 to 32. We also try to increase the number of the GNN model from 3 to 5. But it does not have any effect to the accuracy, so we just stay at 3. We increase the number of training epoch from 20 to 50. All of the improvement and the spending in the training set and the model have a lot of impact to the prediction accuracies, as shown in the following figure. So this figure shows the change in the prediction accuracies comparing to the base model, which is the ensemble of the GNN model, without any improvement or expansion. And the training set is star-shaped topology. We observed that this improvement and expansion on the training set and the GNN model really have to improve the accuracies to 5.3% on average. And at most it is 11.9%, which is we consider it to be a very significant improvement on the accuracy. And what we also observe is that the increasing in the size of the training sets is the most important factor to improve the performance. And just one exception for the testing set 13, because this testing set is just AVB traffic and it's missing in the training set. Next is the execution time of the GNN model. On a single GPU, the ensemble of 32 base GNN model on 1000 distinct configurations will take 21 seconds, and the expanded model will take 32 seconds. So we have some remark on the execution time of the GNN model. First, the improvement and expansion on the GNN model has low impact on the execution time. It's increased to almost 32%, but the absolute time increased is only 11 seconds. And second, the ensemble of the best models still have speed up factor, even though it will be a bit slower than the base model. So it still have speed up factor of at least 50 times and at most more than 1,000 times comparing to schedulability analysis. And the execution time of GNN is always a constant. So it does not depend on the size of the test and configurations like schedulability analysis. And this is one of the most important advantage of the GNN model over schedulability analysis. And finally, this is the conclusion of the study. Our study shows that the performance of the GNN model can be improved with many approaches. Like we can improve and expand the training set, or we can optimize the neural network in the GNN model. And we also show that expand the GNN model with the larger training set is perform better than the other model. So the accuracy is increased on average of 5.3% and up to 11.9% comparing to the base GNN model. And we also note that the larger training set is the most important factor to increase the performance of the GNN model. And finally, the improvement and expanding on the GNN model is increased the execution time very little. It's just up to 52%. But that just means it's increase of 11 seconds for 1,000 test enables. And this study also opened another question of, can this GNN model will be efficient to predict the feasibility in other contexts? It's like we saw with the AVP in the past. Or how about with the multiprocessor scheduling or end-to-end analysis? To answer this question will be a potential direction for the new study in the future. And here's the reference that we use in the presentation. So thank you very much for your attention.